everybody! I hope everyone's having a wonderful day. So, today we're going to be picking up more with 2-4 trees and more discussion of multi-way search trees. So, last day I had introduced you to the idea of how we can insert into a 2-4 tree. So now remember, a 2-4 tree is one for which it has the depth property. That means all the leaf nodes are all on the same level of the tree, and also has the size property, meaning that every internal node has at least 2 children, but at most 4. So the order of a 2-4 tree is going to be 4 at its highest. So you got to think of the order like it's a bound that we maintain. So this value D that we use is often selected, and it's one that we're going to just have set as 4 whenever we talk about a 2-4 tree. Okay, so here's the pseudocode for put. So I'm just going to remind you of the process that we talked about the other day. So you're just going to find that lowest insertion internal node V. So remember, you go down, you hit a leaf node, then you check its parent. That is V right here. Then you're just going to add to V the record in question. And then you're going to check, do I have a 5 node? Is it overflowing? Do I have a muffin top? That is the great question. In my node. So I'm going to check if it's overflowing. So does V overflow? If it does, then what we need to do is do a split operation, right? But just before that, like I had in my example last day, I may have to create a new empty root to put whatever the result of my split operation into it. After this potential opportunity, you're going to then split around the middle key. I'll call it K prime here. And you're going to move that data with K prime up to the parent. And then you're going to update the children by splitting the node into 2. Each one of these will be guaranteed not to have any of these problems with overflowing. And they'll have the size property suffice, because when you're done, you'll end up with it being roughly cleaved in half. And if we know that it overflows at 5, then one of these is going to be a 3 node, the other one's going to be a 2 node. Does everybody get that? And then lastly, I just follow up the tree by going up to the parent and seeing if it overflows at that node. Because whenever I do the split, I push one record up. Remember, you got to think of the 2-4 tree like it's growing up, like a flower. So if this occurs, then you're just going to simply do the split operation again. You're going to repeat until you hit the root, right? So it might overflow at the root and create a brand new root. That is a very real possibility, but you're just going to keep doing this until V just doesn't overflow anymore, right? So the whole thing is this business of overflowing, or where it overflows. So let's talk about the time complexity of put here. Talk about the time complexity. So let's do a quick analysis of this. So finding the node where this would be, how long did that take before? I'm going to write up the time complexities in terms of D and H, and then we'll refine it from there, okay? So what did I do to forget? I used H, it takes H log D, right? To do this, we've seen that the other day. How about adding this in? Well, that takes linear in the number of elements in my array, which will be at most D, but the length of the array is in fact D. Now we have this business here. Let's look at what's happening inside of the loop. So how many operations can occur in here? Is it going to be something in terms of D, or is it constant? What is it? Well, it's quite simple. This is just, I might have to adjust around some things. So I might have to adjust some of these arrays that I have for my secondary data structures. So how long does that take? Well, assigning a new root, well, that can be done constant time. I might have to shuffle things around though. So around the split operation, this stuff might require me shifting around some elements in an array to accommodate as I split to 2 nodes. So all of this together is going to take big O of D. It's just some manipulations of the data over the arrays, but it's definitely not happening more than once or twice. They're just linear scans of these arrays where I do manipulations by shuffling elements around, right? Then I just create a couple of nodes. So, now how many times can this happen? Well, I could start off really at one of these lowest insertion internal nodes, which is really close to the bottom of the tree, right? So I might have to work my way all the way up the entire tree. So we know that this probably has to take in relation h, the height of the tree. So how long is this all going to take together? This is going to be big O of h times d, where h is the height of the tree. So what's the most, what would here be the overall running time then in terms of big O? How long would it take? Well, you can see right here that this h times d is going to be what is kind of the wheelhouse of this whole algorithm. So the big O of h times d. Now this is more general. Now you might ask, okay, well, Dan, you could have said more specifically not just a middle record, which is true here. Remember, I'm going to say that this pseudocode is rather general because we're going to have the same idea up here later in this lecture. So I can specialize this, right? We know what h and d are, right? Since h is big O of log n. Remember last day we proved this. And d is equal to 4. D is equal to 4. Then put takes big O of what? If I could just put h and d in, I have them right here. It's going to take big O of log n. Because d is a constant, and h is big O of log n. So, insertions are efficient on this tree. So for the 2-4 trees, it's rather straightforward. Now, I'm going to shift gears. So let's finish to talk about insertions into a multi-way search tree, in particular our 2-4 trees. Because we're going to have these split operations to ensure that we don't have any fat nodes, okay? So, what am I going to do? I'm going to shift gears to talk about removals. Now, last day, I was kind of vague on what exactly I meant by replacing with the successor, because we aren't talking about a binary search tree anymore. We're talking about now 2-4 trees, but I'm going to keep this discussion general to multi-way search trees so that you can think of this as an aside. This just gets you to think about things. So, there's kind of really two big cases that can happen. So, if this is the situation for which you might need to replace the successor. So, I first have some potential first child here. Now, this can be anywhere within this node here. The key is that there is some left child with respect to x here, which is just some record with some key. I'll call it x. And it has, with respect to x, some right child, so just the child that's actually related to x. So this is x's child. And then I have y that's following right after it. So what would you do normally if you just were to look at it like this, as a binary search tree? What would you do? Well, you would just go down here, you go to your right, which would be your child with respect to your position. Remember, this is associated with this subtree. What would I do? I would go down this one. I would find the successor, and I found it is called Z, so whatever Z is. What would I do? Well, I would just take Z out of here. I would replace X with Z. And then I would delete Z in here, right? So if I delete Z here, the great thing is that now you're in here. And the great thing is it's already it went all the way down to its left, and the deletion is trivial, right? So within this node here, you would have it where you went all the way to your left, so you have went all the way down to your left, and there might be some other stuff here, and then I have Z right here. I could just simply chop that off, right? because it has just this leaf node right here, right? Naturally, if this all goes away, then you have to update just with respect to the parent, just like you would have to do with a binary search tree. But I'll talk more about that in a moment. The big point is that go all the way down to the left, and the fact that this exists, there exists a successor down. Do we ever, when we're doing our removals, ever go up the tree? No, right? The only thing that happens is if you ran out of possible children and all these became leaves here, you would just delete the node outright, just like in case 2 with binary search trees, right? So you never go up the tree, you just delete the whole node, right? So, that being said, this would be how you would deal with replacing the successor and deleting it. Now, in contrast, that may not happen. And I said, hey, look, it's only if you need to do it, right? Okay, so what do we do if I don't have a child that's associated with my record that I want to delete? Well, look at this. This is actually perfectly safe for me to just delete outright. What I do is quite simple. I just get rid of this, so this all can go away. Remember, like my piece of paper, I would do something like this. I could just move this left subtree now to be with respect to y, its child. So I would shuffle over everything this way or that way, depending on which way I need to shuffle things. So the result here would just be quite simple. It would just be, okay, now I have y, and then now it's left to its left, the child that would be preceding this one here. And there might be something else going on over here. I may have it where this is now belonging just before y's child. Did everybody see that? So it's trivial to remove things like this. So you don't have to replace the successor. You can also think of it like I'm replacing it with the successor by just simply deleting this because it's right beside it. This is like case 2 of the successor. But you don't have to think about it like that at all. It's trivial. In contrast, here's the most extreme version of this case. It can look a lot like this. Now remember, I always get the successor, but it's very possible that I could have it where the left subtree off of the child preceding whatever could be the last record in a node. It might not necessarily have any subtree to its right. Keep in mind, this can happen after several upon several deletions. What would you do here? Well, this is the great thing. This should look familiar to you. This should look a lot like when we did things with a binary search tree. This literally looks like case 1, doesn't it? So remember, you think of it like now I have 2 children. I pretend this doesn't exist, right? And then what did I do? I move this up, and then it becomes a child of the parent, or it becomes, in fact, whatever the root is of this subtree would become the root. Does everybody see that? So, that being said, does everybody see how we could do this operation? So I'm just giving you an idea. Now, I'm still not going very precise with this. This is just meant to get you thinking. So that brings me to now talk about removals. The point is that this is not actually that sophisticated. So when we're computing the successor, we have that third case. That third case ain't going to happen just like with binary search trees. In fact, when we do a removal, right? However, this first case, the big thing I want you to observe is that for a 2-4 tree, can I ever have that situation happen on the right in an internal node that has anything else going on in it? Meaning that there is some subtree kicking off of one of the records. Can that happen in a 2-4 tree? Can it? It can't really, right? If it does, you can guarantee that there is, in fact, a successor, and it's in a subtree off its child. Why? Because remember, the depth property guarantees that all the leaf nodes are going to be on the same level. So if I can easily check if I just need to delete mine just like a trivial deletion, or if I need to go down my child to get the successor and replace it and then do the deletion after I computed the smallest off that subtree. So 2-4 trees, you don't have to worry about all these weird cases on a removal. If you need to do the successor, you just simply check your child and find out, hey, look, is that a leaf node? If it is, then I know I can replace it with the successor. I better do that, otherwise I'm going to violate some nice property that the tree has. Okay, so let's talk about removals in a 2-4 tree. Okay, so now let's back to just talking about 2-4 trees. So that discussion was mostly for multi-way search trees in general, but I felt like I wanted to talk a little bit more about that. So a 2 node, remember that's one with how many children? 2 children. How many keys does that one have? It has 1 key in it. A 2 node may become a 1 node. So remember, this is one with no keys in it. That means I've deleted all records from it. This is what I alluded to the other day. Can we have 1 nodes in our tree? No, that would violate what property? The size property. So whenever we do an operation, before we have perform the operation and just after it, it has to be that our 2 properties are maintained and our definition of a multi-way search tree is still satisfied. So, this of course violates the size property. The size property. But you might also notice that if I just were to say, I'm just going to delete that node outright, which is what I was kind of alluding to maybe doing at some point with a general multi-way search tree, that would violate what other property? The depth property. So you can't just delete this. We can't just delete it. We can't just delete it as it might violate the depth property. There are only specific cases where you can't actually do this safely without violating the depth property, right? Okay. So we're going to have a special name for these 1 nodes. So a 1 node is said it underflows. So it has an underflow or it underflows. So if a 1 node occurs, we say it underflows. Now, there's a couple of things you have to keep in mind. Remember, we might have siblings, right? There might be siblings for this node. So what I would do is I might have a sibling for my 1 node, and I want to try to look at them like one big family. So one thing that can happen is imagine I have a couple of keys up here, and then I have some key K2, but so say this is my 1 node right there. I'm going to call this one key 1. Now, if I looked at this situation, I want you to think about this. Imagine if I had 2 siblings possibly beside V here. So V is it underflows. I would look at my siblings, and if both my siblings did not have a key to share with me, or a record to share with me, what would I do then? As a parent, I would say, hey guys, work together, okay? I'll come and supervise. So if I don't want to violate the depth property, I cannot delete this because this node also exists, right? I would violate the depth property. So what would you think of trying to do? So we're going to have one case here. So one possibility is where we're going to need to do something called a fusion operation. If both adjacent siblings, because remember, it can have many siblings, but remember, we need to make sure we maintain the properties of multi-way search tree, right? We want to make sure that these records have their keys still in sorted order. So if both adjacent siblings, siblings of V, were to have one record removed, they would underflow. So like in this situation, you'll notice that if I were to get rid of that, they would underflow. But imagine you have both your siblings that are right beside you. So there could be one over here. I'm just drawing it in a picture just with one. I just picked one of my siblings. They would underflow. So i.e. in our case for a 2-4 tree, these would be two nodes. So nodes with two children with one key. Obviously, I cannot just like take one from one of those and borrow it, right? So what would you do? We need to fuse some nodes together. So what are we going to do? We're going to merge V and W, and then we're going to bring down the parent of V, its associated record here, which I know where it could possibly be. And I'm going to bring that and put it down into this new merged node. This is what's going to be called a fusion operation. Now it's worth noting that K and K prime may not necessarily exist, so just be aware of that. I'll come back to that in a moment. So if I do a fusion operation on this, what am I going to do? I'm going to have K and K prime up here. And I'm going to fuse V and W together. I'll still call it V to make it simpler for you. So I fuse V and W together, and I bring down K2 into my node. But does this underflow anymore? No, it does not underflow. And in fact, it maintains the ordering that I want while still maintaining the depth property. Does everybody see that? So all I've done is I've brought down K2 after I've merged these two together. So now I just end up with one single node that's the child of K here. Now remember, K might not necessarily exist, so underflow may occur at a parent afterwards. Why? Why would that be the case? Think about it. If I grab one of those records and bring it down, now I've reduced the number of records in the parent. Say if I have parent U here, I might reduce it down by 1. What if K and K prime don't exist? Then it's going to underflow, right? It underflows. So in this situation, we needed to fuse some nodes together. So that being said, that's one possibility, is this fusion operation. Now, another possibility is, now if I look at this picture that I have here, there's also the possibility that I may have actually a sibling that does not underflow if I indeed have actually something I can borrow from a sibling, one of my adjacent siblings. So the second possibility is a so-called transfer operation. So I'm going to slightly tweak this picture. Let's slightly tweak this picture. Just to make this simpler, I'm just going to use the smallest possible node I can possibly have in this situation. So I'm going to have a 3-node here. I'm going to have K1 and K2 here. And I'm going to call now the parent K3. And what am I going to do in a transfer operation? So this situation occurs, so if an adjacent sibling W has enough records to not underflow, we can borrow a record from W. Now, I should use the quotation marks borrow. It's more like a supervised lending because we're not actually going to get a record from W directly from this operation. We're going to get it actually from the parent. So the way you got to look at it is like if I have a family dispute and I have like 2 small kids or something. V doesn't have anything and W has all the toys. The parent is saying, hey, you need to share with your sharer, okay? So the way it works is that to punish this child, the parent takes away a record from the child here, and then the parent gives this child a different toy. So what is that going to look like? So we're going to move the appropriate child up, and then we're going to bring one down from the parent using a transfer operation. So what do? So I have my parent U. Now remember, K and K prime still may not exist. So what am I going to do? I'm going to take K2. I'm going to hand it up to the parent, like a toy, from that child there. And the parent's going to give K3 over to V. Do you see how this won't violate any of the properties of a 2-4 tree? We're not going to have to delete V. That's not going to underflow because now it's just a 2-node, right? And we still maintain the ordering because we pushed up the next smallest one, right? So, as a result, I end up with K1. Okay, here, so W. And I have K3 here. And that's V. Now I have a question for you. This looks strangely familiar, but I'll let you think about that while I do something to help you jog your memory when it comes to this stuff. So the way I like to think about this whole thing is involving borrowing things from a family member. So I here have some painter's tape, I have an umbrella, and I have a textbook. What I'm going to do is I want to kind of illustrate these motions using these 3 pieces of lovely equipment here. So when I do things like a fusion operation, I think of how I would borrow things within a family here. Okay, so what would I do if, say, this is my child here that doesn't have anything to play with? However, this child has something to play with, but won't cooperate and give it to their brother or sister. Well, the parent might say, hey, look, you got to share with your friend, okay? So the parent might pull in and give you something else. So what happens? A fusion occurs where they're going to put all their toys together, and then the parent will put in another toy so they have enough toys to play with. So that is how the fusion would go down. In the alternative situation, what could happen is I could have it where one of my siblings actually has more than enough toys, but it's being really greedy. So what would need to happen? What would need to happen? Well, the parent would need to take away the toy from the greedy child. Oh man, I did not prep this in advance, by the way. Then, what happens? Then, the parent gives a toy to the child. And there we go. So now all the kids have some toys, and the parent disciplined the greedy child. So that's one way I like to remember it, is this motion where you think of the greedy child versus the children that don't have enough toys. Have you thought a bit about why this looks somewhat familiar to you? Does this remind you of something? This looks a lot like a rotation, doesn't it? So think back to AVL trees when we did rotations, where we promoted and then we demoted records. This actually is no coincidence. Believe it or not, 2-4 trees have a very intricate and lovely relationship with red-black trees, which also invoke types of rotations. So that's one way to easily remember how a transfer operation works. It's a lot like a rotation. So note that this obviously can transfer one direction or the other direction. The point is that you know which one underflows, and you check your sibling and you do the appropriate transfer either this way or that way. Okay? So does the transfer operation cause the parent to underflow? No. Remember, before it did not violate that property. So after, notice that the number of records up in the parent has not changed. The only thing that's changed is between the siblings here. Does everybody see that? Is that neat? So the big point here is that those are our two main operations for when we do removals. So let's do some examples here. So I prepared this in advance, so please draw down that tree. I was about to call it a triangle for some reason. Okay. So let's do an example here. Let's try removing 9 here. Let's put all the things we've talked about into practice. So let's remove 9. So what do we need first? It's an internal node. None of its children are leafs. I can know it very easily by just checking its direct child. So what do? I need to find the successor of 9, which is what? It is 10, right? So what I do is I copy the record with key 10 up here. So now that's 10. And now I delete this node. So now I delete 10. Remember, usually you delete the record that the child associated with the record. So it would always be the one that's slightly off to the right. And what happens? Is this okay? Is that okay? No. This underflows, right? However, what should we need to do here? What do we do? I look at my siblings. I only have one other sibling for this node. So this is node V right now, right? So I check my sibling. Look, it's a 3 node. So I can borrow a record from, this is W right here. So I perform a what kind of operation? A transfer operation. So what I could do is I can promote, I can put 16 up here, and I can bring down 15. Now, one very, very touchy thing you should be noticing is that there's something that still has to happen with this right here. This is why I say it reminds me a lot of a rotation. Is, remember, you got to think of it like our counterweight in a rotation. This little weight needs to go over here. Remember, this could potentially actually be a subtree somewhere if this were to occur further up, okay? So, because remember, a transfer doesn't necessarily have to happen at this level. So this is going to now be on that side. And now this is gone. And now that's up here, right? Remember, think of the motion. I promoted up 16, I've demoted 15. Just like when I talked about a rotation. So there we go. So that's nice and easy, right? Let's do another one. Let's remove 17. Okay, let's try removing 17. So now I have 17 here. I find it, it's right here. So notice its child is a leaf. That means that we can safely just delete this record along with this associated leaf. So I can just go like this. I don't have to remove or replace anything with the successor. Do I delete this? Remember, maybe I shouldn't do that quite yet. Remember, I can't delete this node, otherwise it's going to cause problems. This is no longer going to be a 2-4 tree. However, is this okay? No, it underflows. Now, can I borrow from a sibling? No, I need to work together with the parent and my sibling. Here, I have one sibling, so what I'm going to do is I'm going to fuse together V. Actually, now V is right here, right? V is right here, W is right there. I'm going to fuse this record from up here, this, and all that together. So I end up with a single node that's going to have 15, and it's going to have 16 in it. And then, let me just fix this up a little bit. So what should I end up with? It should look something like this, right? So now V and W have been fused together, and now it's one node with, oops, I think I'm missing a leaf here. There we go. Sorry about that. So now I've done the fusion. Where do I go next? I need to go up. So I go up. Now this is going to be V. Is that okay? No, it underflows. So what we're going to do now, what can I do? Look at my sibling. This is W. I just look at any one of my siblings as long as I check both of them. They have to be the adjacent ones. I can't just check one that's like way over there or something. Okay. So I look at this. Okay, what kind of operation should I do? Transfer or fusion? I should do a transfer operation. So I'm going to bring 5 up, and I'm going to bring down 10. 10 is going to go here. 5 is going to go up. And where does this go? Where's this dangling guy going to go here? It's going to go right there. Did everybody see that? So I passed it over just like in a rotation you would do such a thing. And we're done. Look at that. So I can do a fusion. Fusions can occur more than once. However, a transfer only can happen once in a removal. Once the transfer happens, you don't have to worry about any more exploration up the tree. So as long as the node does not underflow, you're okay. So that's how you remove from a 2-4 tree. So let's look at the pseudocode for remove. We'll do the analysis. So I've written it up in advance, and we're going to walk through this. And like I said, I made it very general because we're going to use the same pseudocode later on when we talk about the final data structure in this class. So here's remove. It takes in a root, some key, and it removes the data record with key K. So what's the first thing you do? We find the node. So we just find it, and then we're going to remove it, and we're going to try to replace it with the successor if we need to. Remember, earlier on I told you about when you might need to do that. In a 2-4 tree, it's very easy to check, right? Remember, if I know that my child associated with that record in the same position on the array, if that is in fact going to be one that is a leaf, then you know that you don't have to replace the successor, okay? So you can just trivially just delete it and to just shuffle things over, okay? So, that being said, if the successor is replaced, then wherever the successor was, that is where V is going to be now. So all the cases that we've been talking about all really can be reduced down to where all the children are in fact leaf nodes, if you really think about it. Because if you ever have to go down to the successor, you're going to have to do these more complicated operations because a trivial deletion like this, it will happen more likely down here. So it's worth noting that if you do deletion from here, you could potentially have an underflow. But when can it happen in an internal node? It's when I go down, right? I have to delete the successor, right? That's why I'm saying that. So while node V does underflows, we're going to do the following. We just break that down into cases. Now, one thing I believe I didn't show you in my examples here is that there might be a possibility we might literally destroy the root. So if V is the root, remember now it's a one node, it's just sitting there. What you're going to do is you bring up V's first child as the new root. So you just go down, look at the children, and then just pull it up, bring it in there, and then that'll allow you to have two children again. So if that happens, not too tough. So these are our two cases. So first I have it where our transfer is going to occur. I just check if there's a sibling, and I call it W like in my examples. If it has at least the ceiling of D over 2 keys. This is in more general terms when we start talking about D more arbitrarily. Remember, D is 4, so this is just really where it has at least 2 keys for a 2-4 tree. So if it has at least 2 keys, you know what? You can borrow one of those records, right? So you do the transfer operation with W, V's parent, and V. Otherwise, you're going to perform the fusion operation with W, V's parent, and V. And you're going to just simply go up the tree to the parent. Because remember, transfers will not cause underflows after. However, the fusions can. So once this comes back around after a transfer, you'll see, hey, look, there's no underflow occurring here. However, this could potentially happen after a fusion operation. Okay, so let's talk about the time complexity of remove. Let's talk about the time complexity. So, finding this right here. What was that? That's H log D, right? It's going to take big old H log D. Then what? Removing this, how long does that take? So doing all of this, remember, we said last time that this is going to be D plus H log D. So D plus H log D. Now, how long does it take to perform a transfer or fusion operation, or say change around the root? It's all really just shuffling around elements inside of arrays, right? It's either creation or deletion of constant number of nodes. However, most of the work is just manipulating the data appropriately so that we maintain the structure. How long does that take? All of this should take big O of D. So remember, I'm either cleaving or I'm moving things around. Now in a split, it's literally cleaving. In these cases, I just grab the appropriate information and then I put it all together into a new array. How long is that array? It's in terms of D, right? In a transfer, I just simply need to update elements by shuffling things around. That also takes linear time in D, right? So it's linear in D. How many times can an underflow occur? Well, it could potentially be almost the whole height of the tree, right? Like it can keep going all the way up where underflows keep happening. All the way up the tree. So what does that mean in total? This better be big O H times D, just like we had before. So the overall time complexity, if you look at all of this, what's the most dominant term here? Is it D plus H log D or is it HD? It's high definition, okay? It's high definition. HD. Wherever H is the height, D is the order of the tree. But remember, we can be more specific here. So this analysis applies more broadly with an arbitrary D and an arbitrary height. So again, H is big O of log n, right? And D is equal to 4. So remove takes how long? It takes big O of log n time, right? So another log n operation. Isn't that great? So we can do insertions, removals, searches, all in logarithmic time, just like what we had with the AVL tree. Except this is far more general, right? So, where does that bring us next? Where are we going to go next with this? Well, I'm going to take the structure that we've talked about, the 2-4 tree, and I'm going to generalize it even further. So, what I'm going to do is I'm going to first introduce you to this more general concept. I'm not going to tell you too many details, and it's going to get revealed as we explore through this final structure we're going to talk about. So, the final main data structure and the main topics of this course is the B tree. So we're going to talk about B trees. So I should mention for historical reasons, this was developed at Boeing by Bayer and McCreight. So this is like 1970 we're working our way up to. So this is like 1970, Bayer and McCreight. This is at Boeing. You'll find very often a lot of these industrial or military-based applications. So I'm not sure if it was military at Boeing, but Boeing does a lot of engineering and all sorts of neat things involving technology, especially during that time period. You'll find a lot of the applications out of early optimization work tends to be tacked on a lot with military research and things of that nature, among other things. So, like for example, with the minimum spanning trees, we've seen how the application of distributing power or telecommunication lines was vital. So we need to do that optimally well, right? Or at least something like that. So we're going to talk about B trees. So a B tree belongs to some of the best known data structures for maintaining data in terms of external memory. So imagine if I have a dictionary, I want to maintain this thing in external memory. B trees are one of the best known in the class of data structures for doing things of that nature. So a lot of the data structures we talked about, they could be suitable for doing things with external memory. But the B tree is kind of like the king of the structures in that class. So it's one of those kingpins in that area. So what's a B tree? So it is a multi-way search tree. Search tree with order D. So the order can be arbitrary. So it can be D, whatever. You get to pick what D is, or you can let D be arbitrary if you want it to be. such that 1, so you're going to find that this is going to generalize over the 2-4 tree. You'll see in a moment. The root of t has at least 2 children and at most d children. So at least 2 and at most d for the root. So the root is going to be a little special compared to some of these other ones. The number of children, every internal node so the number of children every internal node must have is at least the ceiling of d over 2. So remember, round up d over 2. At least d over 2 and at most d. And finally, the last one, it satisfies the depth property. So all leaf nodes are at the same level, are same as sort of melted in the microwave, same level of T. So let me draw you a picture of one. Okay, so there is the B tree. That's my example. So let's see if this follows the definition of a B tree. So first, the root has at least 2 and at most D children. Has at least 2, we're okay. The number of children every internal node must have is at least the ceiling of D over 2. So first off, we need to determine what D is. What's the D in this tree? If I were to decide what the order of this tree is, what order does this tree have? What's the maximum number of children do I got here? What is it? What's the maximum number of children do I have in this tree? Let's find out. So I've got 2, 3, 4, 3, 3, 5. I got 3, 1, 2, 3. I have 4 on this one, 3, and 2. So the order of this tree is 5. So that is order 5. Remember, we look at the maximum number of children for our order. Notice I have 5 as the maximum. So, notice that if I got rid of 5 here, this would violate this property, right? Why? Because now this would have 2 children. Because now, remember, the ceiling of 5 over 2, remember 5 over 2 is 2.5, right? But that's 3. So, that means if I get rid of 5, that means this has 2 children, which would violate this property, and this is no longer a B tree. And all of them are on the same level? Okay, so now do you see why this is a generalization of a 2-4 tree? Well, just simply put, D is 4. Is when D is equal to 4. Does everybody see that? So when I just make D 4, that will guarantee that there's at least 2 and at most 4 children, and they're all on the same level. So this is really just a generalization of the size property, right? So that's our definition of a B tree. Next time, we're going to talk about B trees, and that will wrap things up. So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.